Okay, this is exam 4 is our free response. The diffraction grating has 2,500 lines per centimeter. A green laser of light 520 nanometers shines on the grating. What is the separation first of the lines? So my separation D is going to be the inverse, pardon me, the inverse of the 2,500 lines per centimeter. So 1 over 2,500 lines per centimeter. That'll give me the number of centimeters per line. So that's 4 times 10 to the minus 4 centimeters are 4 times 10 to the minus 6 meters, which are going to be, so 4 microns. What is the distance from the central maximum to the second order fringe? So a couple steps here. First, we need to find what is theta. So we say d sine theta equals m lambda. And so theta is going to be the inverse sine of m lambda over d. M is the central maximum to the second, so M is 2. Lambda is, what was it? 520 times 10 to the minus 9 divided by the D, which is 4 times 10 to the minus 6. So that gives me 15 degrees. And then I want to know the distance to that, so I say y equals L tan theta. Do I give the, oh, I don't give the distance between the screen and the slit. Okay, we'll let this, I'll include this, but we'll have L is equal to, I don't know, how about 3 meters? So that's going to be 3 meters times sine, or tan of 15. 3 times tan of 15. I get 0.81. So that is the separation. So if I were to draw this distance is going to be 0.81 meters. And then finally, how many fringes are present on the screen? Remember that the last order number is when theta is equal to 90. So I would have m is equal to d sine of 90 divided by lambda. So that's going to be 4 times 10 to the minus 6 divided by 520 times 10 to the minus 9. And that is 7.7, so that rounds down to 7. That means that there are 7 here on this side, 7 on that side, and then the 1 in the middle. So it's going to be 15. That's 7 plus 1 is equal to 15. So that's the answer, 15.81. And then this 4 times 10 to the minus 6, so I'd take it in centimeters as well. Consider this system of 2 lenses. What is the magnification of the final image? So for A, I first have P1, F1. I want to find Q1. That's going to be 1 over F1. That's 1 over 20 minus 1 over 30. The inverse of that, let's see, that's 3 over 60 minus 2 over 60. It's 1 over 60, so Q1 is equal to 60 centimeters. That means that my final, oh, and then my M1 is negative Q1 over P1. That's negative 60 over 30, which is negative 2. So my second image, or my first image, is going to be right here. It's going to be twice as big. It's going to be inverted. It's going to be 60 centimeters from here, so 10 centimeters from here. Now, I find Q2 is going to be 1 over F2, that's 1 over 5, minus 1 over P2, that's 1 over 10. So this is my P2 to the negative 1. That's 2 over 10 minus 1 over 10. That's 10 centimeters. And then M2 is going to be negative Q2 over P2, which is negative 10 over, 10. So it's negative 1. And then the total magnification is going to be M1, M2, which is negative 2, negative 1, R just 2. So that's the answer. And this final image is going to be, let's see, where is it? 10 centimeters to the right. So it's going to be here. It's going to be twice as big as the first image, but upright. So for B, this is really part of A, but the final distance, Q2, is 10 centimeters to the right of the lens. All right, and then here an object is 4 centimeters high. Height of the object is equal to 4. Spherical mirror produces an image of this object that is 2. So height of the image is 2. And on the side of the mirror opposite the object, that tells me that Q is a negative number, that this is a virtual image. And the mirror has a center of curvature that is 30 centimeters. So C is equal to 30 centimeters. Now, the first thing I want to recognize here is that my magnification is 2 over 4. And because it is a virtual image, because it's on the side opposite the object, my magnification has to be positive. Okay, so if it were negative, then that would tell me something about the mirror that's producing this image. But since it's a positive magnification, it's an upright, virtual, smaller image, that tells me that this mirror is a convex mirror. The reason is because of this magnification is positive 1/2. And that mirror, my object is here, my image is here. That is a convex mirror. And then also wrapped up in this, is it a real or virtual? It is a virtual. It is upright and it is smaller than the object. Now I want to know what is the image distance. So to find the image distance, recognize that I know the magnification, it's 1/2, and that that's equal to negative Q over P. I also know the focal length because the focal length is equal to half the center of curvature. So that's 30 over 2, which is equal to 15. However, because this is a convex mirror, my focal length is negative. Okay, so what is the image distance? 1/2 equals negative Q over P. 1 over negative 15 equals 1 over Q plus 1 over P. I have these two equations, and I can solve one for the other. I want to know what is Q, so I'm going to say P is equal to negative 2Q. All I did was cross multiply there, and I got an expression for P that's in terms of Q. And now I can put that in for P. So I can solve this. 1 over 15. I find a common denominator, which is going to be 2Q. So it's going to be 2Q, 2 minus 1. That's the same, right? Yeah, 2 minus 1. So negative 1 over 15 is equal to 1 over 2Q. So Q is equal to negative 7.5 centimeters. All right, let's look at the multiple choice now. Explain why astronomers use a parabolic mirror for large telescopes instead of a spherical mirror. Not because it's easier to create, although that is true for some telescopes. Remember the Mercury telescope I was telling you about. It's not because they do not experience chromatic aberration. Spherical mirrors don't experience that either. It's because they all focus at the same focal point. Remember with parabolic mirrors, light rays focus there, and then light rays coming in the middle will focus at the same focal point. They do not experience spherical aberration. For your eye, the focal length can change. For a camera, the image distance can change. What is the focal length of a magnifying glass that produces a magnification? Equal to 2 when held 4 centimeters from an object. So P is equal to 4. I think this is an OpenStax question. You should realize this is a convex lens, so the focal length is going to be positive. Looks like they're all positive, so it doesn't help us. And then also the magnification is also positive because convex lenses produce upright virtual images that are larger when you're using them as a magnifying glass. So there's our focal points there. I'd put my object there, and my image would be right there. It would look like that, bigger and upright and virtual. Okay, so 2 is equal to negative q over p. I know that p is equal to 4, so I just put in a 4 right there. So q is equal to negative 8, which jives with what I know, that it's a virtual image. And now that I know q, I can find the focal length. So I say 1 over p, that's 1 over 4, plus 1 over negative 8 is equal to 1 over f. So f is equal to 8 centimeters. If an object is 12 centimeters viewed through a lens with a magnification of 3, what is the height of the image? This is the height of the object. It's multiplied times 3, so it's 36. M is HI over HO. So I have 3 is equal to HI over 12, so HI is equal to 36. To create a real image with a lens, where should you place the object? To create a real image with a lens, you place it outside the focal point. You can only do this with a convex lens, and if I put it there, let's see, I trace my rays parallel to the axis through the focal point, parallel to the axis, there's my image. This is my object, this is my image. The object is 6 centimeters from a convex lens along its axis. The lens has a focal length of 9 centimeters. So let's see what I got here. I got P equals 6, F equals 9. Oops, sorry. 9. This is a convex lens, so it has a positive F. What are the respective values of the image distance and the magnification? So 1 over 9 equals 1 over 6 plus 1 over Q. 1 over 9 minus 1 over 6 equals 1 over q. You could do this with calculator, but you don't really need to. So this is a 6 over 54 minus, isn't that right? Yeah. 9 over 54 equals 1 over q. So q is equal to negative 18. Let's see, is that okay with what I'm thinking? Yeah, this is, notice that my object distance is inside my focal point. So that tells me that it's going to be a virtual image. In fact, I could go ahead and, knowing that, I could get rid of these. And I could go ahead and say, well, heck, I know it has to be, if it's a virtual image, it has to be upright. So D has to be the right answer. But let's just go ahead and do that. I didn't really need to do this, did I? So M is equal to negative Q over P. That's going to be equal to negative 18, negative 18 over 6, which is positive 3. A mirror has an upright image that is 1/2 the size of the object. If the object is 6 meters away, what is the focal length? Oh goodness, this is similar to what we had here. So M is equal to 1/2. It's an upright image, so it's positive. It's also going to be virtual. Let's see, can I just figure out what this is? Well, I know that it is a convex mirror. It looks like this. And so I can get rid of that and that. Otherwise, I can't really get rid of any of these others. So let's just go. It'll be either A, C, or D. P is equal to 6. So do like I've done before. Have 1/2 equals negative Q over 6. So Q is equal to negative 3. And then F is equal to 1 over Q plus 1 over P. Inverse of that, that's 1 over negative 3 plus 1 over 6. That's 1 over 6, negative 2 over 6, so it's equal to negative 6. C is the right answer. You stand 2 meters in front of a mirror, has a center of curvature of 8 meters. The image is big. What is the magnification? So, this should be mirror. P is equal to 2. F is equal to 4. Is it positive or negative? Well, my object is inside the focal point, and the image is big. That tells me this is a concave mirror, so it is positive. And I want to know what is the magnification. So I have to find Q again. That's 1 over F minus 1 over P to the inverse, just the mirror equation. 1 over 4 minus 1 over 2. Q is equal to negative 4. And so the magnification is negative, negative 4 over P, which is 2, so it's positive 2. Oh, but look, I could have gotten rid of this, this, and that. It had to be either A or D, because I know that it's a concave mirror. I'm standing inside the focal point, and so it's going to look like that. So my magnification has to be bigger than 1, and my magnification has to be positive. Which situation produces a virtual image? Concave mirror without object outside the focal point? No, that's a real image. Concave inside the focal point? Yes, and yes. So A is the right answer. For a mirror, an incident ray that travels through the center of curvature will reflect and go back through the center of curvature. There we go, A. This figure shows an image created by a lens or mirror. What type? There's my object, there's my image. Um, Well, it is a virtual image, and the virtual image is on the same side as the object. So therefore, it must be a lens, cannot be a mirror, because if it were a mirror, the image would be upside down. And it's also bigger, and so that tells me that it has to be excuse me, a convex lens. And so that would look like this. It's like a magnifying glass. My object goes here and my image goes here. Actually, I'm going to change this so that the image comes over here. That would be more correct. Okay, so it's a convex lens. It's like a magnifying glass. Give me just a second. Okay, consider this lens, the object, and its rays. Which ray is or are incorrect? All right, well, this one goes through the focal point, and then it goes parallel to the axis, through the focal point, and that one goes straight through the center of the lens. So all of those are correct. E, all are correct. Diffraction grating has 2,500 lines per millimeter. What is the slit separation? Oh, we did one very similar to this on the free response. 2,500 millimeters. That's going to be 4 times 10 to the minus 4 millimeters, which is 4 times 10 to the minus 7. Okay, how many bright spots are on the screen here for this diffraction grating? Remember, when I'm doing this type of problem, I set theta equal to 90 because if I have my diffraction grating and I have my diffraction pattern, these light rays are traveling at angle theta. However, when my angle theta exceeds 90 degrees, then it's like the light rays are going behind the diffraction grating. So I can't exceed that angle. So I say d sine theta equals m lambda. So m, since theta is equal to 90, sine of 90 is 1. M is d over lambda. So that's 1 times 10 to the minus 6 divided by 500, 10 to the minus 9. That's 2. So my diffraction pattern looks like this. I have a second order on both sides, so that means I have 5 spots altogether. You have a double slit and you want to make the fringes further apart, what could you do? Look, d sine theta equals m lambda. To make them further apart, that means that I'm increasing theta. And so if I increase the slit separation, as if I increase d, will that make theta increase? No. But if I increase the wavelength, that makes theta increase. If I decrease the slit separation, that makes theta increase. If I decrease the wavelength, that doesn't do it. So it's 2 and 3. A is the right answer. Two waves travel through space. The first wave travels 8 meters. The second wave travels 10 meters. When they meet, total destructive interference occurs. So they have a path length difference equal to 2 meters. And I know that that path length difference has to be some, pardon me, let me stop for just a second. I want to check something. Okay, I'm going to change this problem. I'm going to change it to these numbers. 7 meters is the wavelength of the first, or excuse me, the distance the first wave travels. And then I'll change it to these options. The previous one wasn't incorrect, but I just like these numbers better. So I have my path length difference now is 10 minus 7. That's 3 meters. Now I know in order for total destructive interference to occur, the path length difference, PD, has to equal to a half a wavelength, 3/2 of a wavelength, 5/2 of a wavelength, and on and on. So, like this one, A, for example, that's just one wavelength. This is two wavelengths. Um, let me repeat that. 3 meters, the path length difference, is one wavelength if that's what that is. 3 meters is two wavelengths if it's this. 3 meters is what, like 5 point something wavelengths, 5.67 or whatever. But here, if my wavelength is equal to 2 meters, then the path length difference would be 1.5 wavelengths. 3 meters would be 3/2 of a wavelength. So the answer then is going to be D. So I'll change number 16 to have those numbers. Number 17. Here the wavelength is 2 meters. What is the path length difference? So let's see. I'm 1, 2, 3. So that's my third order. And then this is another half wavelength over, so it's 3.5 wavelengths. My wavelength is 2, so it's going to be, I'll have to come back and change this. I'll change the numbers on this, number 17. And then by what amount are these two waves out of phase? These two waves are out of phase by 90 degrees. Single slit is used to create an interference pattern on a screen. If you increase the wavelength, what happens to the width of the central bright fringe? A sine theta equals m lambda. If I increase the width of the central bright, or excuse me, if I increase the wavelength, if I increase this, the angle theta will also go up. So if I increase the wavelength, it gets wider. Who's my favorite student? Look, I like all these students at various times, but love all my students. So